Hello. Now, I have no idea whether you can actually hear me, so if somebody could comment yes or no, that'd be good. Otherwise, I'll be talking to myself. Yay, nay, can you hear me? Ah, there we go. Abby can hear me. How you doing, Abby? Now, I'm noticing a slight anomaly here because you're not actually in my class. Dylan can hear me as well. Fantastic. Who shared the link with Abby? Ah, never mind. Right, okay, we've got 5 of you here at the moment. The work I set earlier, and again, I'm not sure how relevant this is going to be to you, Abby, because you weren't set the same work, but we'll go with it anyway. I didn't get too many questions on it. The questions I did get were mainly related to Stefan's law and question 4 of what I set. So we're just going to have a look at those. Hi, Paula. How you doing? So Stefan's law. It's very high tech. Now is that backwards or is that the right way around for you? Am I gonna have to write things in mirror image? Hi Joe. Somebody tell me that's backwards on my screen. Is that backwards on your screen or the right way around? And I will continue once I know. That's fine. Okay, cool. It's backwards on mine, but that doesn't matter. So Stefan's law, I've written this out. So someone wanted this explaining. I'll go through what I think you might be getting at here. So Stefan's law is to do with how the power output of a star, so that's the energy per second that's actually emitted from the star, how that relates to the temperature of the star and the surface area. Now this thing here is just a constant. So in any question, you would just look up that constant on your formula sheet, not a problem. Surface area, of course, you should know how to work that out as well. That's from your data sheet, so that's a geometric thing. Of course, later on, the questions we've been looking at, you've been talking about diameter. Diameter, of course, if we square root a ratio of areas between 2 stars, should we say, then we'll get the ratio of the diameters, because the diameter squared in that equation is proportional to the area. So we'll come back to that. Notice that temperature is to the power 4. Okay, so if we look at the power of our star, that is proportional to the temperature to the power 4. So it's a fairly straightforward equation. It can get confusing because they talk about luminosity and Stefan's law. Remember, power is luminosity. They are the same thing. We just like to have different words in astronomy to make it nice and confusing for you. So power is luminosity. And what does this equation tell us? Well, it tells us obviously that the bigger surface area and the higher the temperature a star has, the more powerful it's going to be, which is kind of obvious. But what it also tells us is that if we were to have 2 stars of the same power and one had, let's say, a smaller surface area, it would need to have a higher temperature. Okay, reducing the surface area wouldn't require too much of an increase in temperature because temperature is to the power 4. However, if a star was cooler and had the same power as another star, then it would need to be considerably bigger to produce the same power output. So that's the sort of things you could be asked about this. Now, more often than not, guys, what's going to happen is you're not going to be given the power of a star, and this is what happens in that question 4 that you were doing earlier. You're going to be given the absolute magnitude. Now, just going back, apparent magnitude was how bright the star appears to be. Okay, so that's the amount of light from that star reaching us on Earth per second. So it's sort of a power, but it's the amount of power that's reaching us. When we talk about absolute magnitude, that is directly proportional to the actual power of the star. So if I have two stars and I'm doing one of these comparison questions and I have the absolute magnitude of both stars, then from the difference in their absolute magnitudes, I can work out what the ratio of their actual power or luminosity is as well. And that's what's going on in question 4. So let me just find that. So these were the questions that you had. You're not going to be able to read those on the screen, but I'll read it out to you. We had 3 stars, X, Y, and Z, and they had surface temperatures of 4,000, 8,000, and 20,000 Kelvin. Let me just make a note of that. So we've got 4,000, 8,000, and 20,000. They are our temperatures, and they are stars X, Y, and Z. Now, some of you, English is not your forte. It says respectively, so it lists them as X, Y, and Z, and so if that is their temperatures respectively, that's in the same order. And the absolute magnitudes -4, +4, oh sorry, -2, I apologize, -2, +4, and +10. So for those of you that have just joined, these this is question 4. So we've got these 3 stars. Let's just have a look first at what's going on here. Obviously, we've got one that's at a very high temperature, but remember the positive numbers for magnitude actually indicate that they are not as bright. And because this is absolute magnitude, that means they are actually not as powerful. So this is the one with the highest power output here, okay, and this is the one with the lowest, the dimmest star. And here are our temperatures. So we know from what we just said about Stefan's law on the other side that we can work out something about the size if we know something about the power and about the temperature. And we do know something about the power because we've got the absolute magnitude there, okay? The question asks, well, list the stars in order of increasing power output for a start. So actually this one was easy. The least powerful is the one with the smallest absolute magnitude. Remember what we're doing here with absolute magnitude is saying, let's pretend all these stars are the same distance away. And this is how bright they would seem. Now, if they're the same distance away from us, theoretically, then the absolute magnitudes will tie in with how powerful they are. So least powerful is Z, and the next most powerful Y, and the most powerful X. So that was part A. The evolutionary stage. Now I've not got the diagram, the Hertzsprung-Russell diagram to hand, but for part B, without finding that and holding it up to the screen, what you would have needed to do for B, state the evolutionary stage of each star. Well, you've got this along the bottom of the diagram. Okay, you've got your absolute magnitude, sorry, at the side, apologies, and you've got your temperature along the bottom, and it's just like plotting a graph. So I would go across from that temperature to that magnitude and see which region of that diagram it falls into, okay? And that region will tell you it's either a red giant or it's a white dwarf or whatever else it may be. So that's how you'd answer part B. Sorry, my phone was ringing there at the same time, so I was distracted. The bit you were struggling with, I think, was C. Calculate the ratio of the diameter of X and of Y relative to Z. So we'd start by saying, right, what's the ratio of the diameter of X compared to Z? And then what is the diameter of Y compared to Z? Now, to do this, back to Stefan's law, if I have the power of each one, what I would probably do is I would start by finding out the ratio of the power to the area, because I can get from the power to the diameter from that quite easily. So to get power over area, this bit's just a constant, so I can kind of ignore that in the ratio because it's going to be the same every time, so it's going to cancel. I want to divide both sides by area, and then I can find out something about that ratio of diameter to area. However, what I don't know is power directly. I know absolute magnitude, so we need to start with that. Now, x to y, we are going from x to z, -2 to +10. That's a change of 12 magnitudes. What does that mean in terms of power? Well, 2.51 is the magic number here. It's a logarithmic scale, remember. Every time you increase the star's power by 1 magnitude, it's 2.51 times bigger. So what I need to do, because I've got a change of 12 here from -2 right up to 10, I need to do 2.51 to the power 12. And when I do 2.51 to the power 12, calculator, 2.51 to the power 12, I get, I can't read it because it's backwards, 62,500 and something. So let me just make a note of that. You could do this with me if you want. So that's 2.51 to the 12. 62,529. Right, what does that mean? That means that star Z, star, too many whiteboards, star X is 62,529 times brighter and more powerful than star Z. Now I want to know in terms of temperature, because what I am going to do is see what happens with the temperature as well. So let's have a look. Calculate the ratio of diameter. I've actually confused myself by having numerous whiteboards here. Bear with me. The ratio of the diameters. Right, okay. I want to get area on its own. I think I mistakenly said earlier I was going to divide by area. I want to know what area is by doing power over temperature. Power, 62,000 times brighter. How about temperature? Well, the temperature of X is 4,000. 4,000 to the power 4, because it's to the power 4 in the equation. I'll answer your question in a second, Sophie. Doing a very good job of confusing myself without reading that at the same time. 4,000 to the power 4 is 2.56 times 10 to the 14. So I'm going to make a note of that. 2.56 times 10 to the 14. That is for star X. And for my other star Z, I've got 20,000. So I want to do 20,000 to the power 4. That gives me 1.6 times 10 to the 17. That is star Z. Remember, X was this many times more powerful. The temperature of X to the power 4 is this. The temperature of Z to the power 4 is this one. So if I want to do the same, I want a ratio. This is already a ratio. This is how many times brighter it is. I want to know now how many times hotter is it. So I need to divide this number by this one. So I'm going to quickly do that. 2.56 times 10 to the 14 divided by 1.6 times 10 to the 17. And I get 1.6 times 10 to the -3. And I'm expecting that number to be to the minus something, because when you look back at the temperatures, Z was actually hotter, even though it was less powerful. So I've just divided X by Z. So I'm getting a negative number there. 1.6 times 10 to the minus 3. Recap again. This is how many times more powerful X was than Z. This is how many times hotter it is. If you want to look at it that way, it's basically the temperature to the 4 of X over the temperature to the 4 of Z. Now I want to put this over this, okay, and that will give me the ratio of the area. Let me write that out. So that's 62529 over 1.6 times 10 to the minus 3. And you might be doing this along with me as well. You're probably not, if I know you. Okay, so that's what I've just done there. My answer is 390800625. Now that is area. That's how many times bigger X is than Z in terms of surface area. But the question has asked us how many times bigger is it in terms of diameter. So I need to do the square root of that. So I'm going to do the square root of my answer. And I get 6,250. And if you looked at the answers, it was 6,300. So you would then do the same thing comparing star Y to star Z. First of all, how many magnitudes difference is it? 2.51 to the power of how many magnitudes you've changed. That tells you how many times brighter it is. Put that number aside, work out the area, how many times bigger or smaller is its surface area. Divide one by the other, the magnitude difference by the surface area difference, and square root. And you'll get the answer for Z1 as well. Sophie said, do we have to know the conversion of brightness per magnitude? Sophie, I assume you mean the 2.51 thing. It's not on the equation sheet. You can work it out from the absolute and apparent magnitude equation if you're sort of okay with logs, but I would recommend learning it because it just makes questions like that loads easier. Okay, so just learn that every change in magnitude is 2.51 times brighter than the last. Any other questions while I'm here? Just type them in the comments. And I've obviously seen YouTube before, so click subscribe to get more like fascinating videos, probably of me playing football with my kids or something. Sophie said, yeah, I don't really know what that means. I assume this might mean, yeah, she's got another question. If anyone else has, just add them on the right-hand side. Yesterday, I was asked a question about Wien's law, you know, W-E-I-N-S law, and people couldn't quite get their heads around that and the mistake they were making. That wavelength in Wien's law, that's not the maximum wavelength, and that's what some people were interpreting it as. It's not the maximum wavelength for a certain temperature of star. It is the wavelength at which most of the radiation is given out. So if I just sketch something that looks vaguely like the graph you had yesterday, you sort of always got this shape where this is your power output, the energy, if you like, on the left, and you get graphs with different things on this axis, but all related to the amount of energy. Along the bottom here, you've got the wavelengths. So what Wien's law is not giving you, it's not giving you the maximum wavelength over here. It's telling you where that peak occurs, okay, at this wavelength here. And what it says is that if you've got you may have noticed this sort of trend going on where your peaks gradually shift this way as the temperature of the star gets lower. Okay, of course, it might help you to think about frequency. This is a hotter star. The wavelength has got lower, but that means the frequency's got higher. And I think that makes more sense to most people. Hotter objects emit higher frequency radiation in general. Paula said, what were the points that you could write for question 3B? Let's have a look at question 3B. I'm getting into this now. I think I might be a bit of a YouTube sensation, if that's a thing. 3B. State the defining characteristics of a white dwarf star and list 2 other properties it possesses. Okay, so white dwarf stars. I mean, if we look back here, what you need to know about these stars, all of them, is this sort of general life cycle. So what happens to a big star throughout its life and how does that end? What happens to a small one? And less often asked, what happens to the medium ones? And you've not got to give loads of detail, but there's a definite sort of route for each one. So for white dwarfs, you want to talk about the magnitude of them. They're not like the most powerful things, okay, because they are what happens at the end of a star's life and not a really big star, a small one. Absolute magnitudes between 15, plus 15 and plus 10. So that's one of the things I would have written. And just something like, they are relatively small when compared to red giants. They have a magnitude of plus 10 to plus 15. That's the ones off the top of my head. Let's see what else we had in the pages leading up to that. Not a great deal on white dwarfs. It's a pretty small section, to be fair. No, I would just go with those 2 and the fact that it's a relatively small, low mass star that would end up being a white dwarf. Okay, so absolute magnitude plus 10 to plus 15, and smaller than the sun. Any other questions? Who have we got here? Joe, Kira, Dylan, Abby Peak. I think we are out of questions. So I'll do another one of these later in the week, depending on how many questions on certain things you've got. If you send me the questions first, then obviously I'll be more prepared for the answers, although that's probably not quite as amusing for you if I'm not. And I will get back to you about your written answers that you submitted earlier by email. I don't think there's anything else I've missed here. No, tomorrow you're going to be looking at those life cycles I've just spoken about. So what happens to a high mass star and how does that end? What happens to a low mass star and how does that end? Okay, and you should be able to plot what happens to those stars on that Hertzsprung-Russell diagram, just general arrows going from main sequence up to maybe red giant and then down to white dwarf, or a different route for a high mass star. So I will go for now. Thank you for joining me. I reckon you can probably watch this again if you need an explanation of that question again. And I'll clean all my whiteboards and get ready for the AS one. Keep safe. Wash your hands. Peace out.